till now you were doing static, means what is the initial tendency of the aircraft after the disturbance followed. Okay, so here dynamic means the time history is required. So with time how the airplane is going to perform. So right, dynamic stability is related to the motion of aircraft to the motion of the aircraft and its time history and its time history, full stop. Dynamics of the aircraft is always involved with oscillations as shown below. Okay, let's begin this. So let's say I'm conducting an experiment in my laboratory. Okay, I have a set of springs. I have a set of springs. Okay, one second. Let me just go. I have two springs of same stiffness. Okay, and I have mounted an aircraft let's say this is my aircraft. One second. Okay, now if I apply some force of excitation to this, what will happen? One spring, that is this one, this spring will get compressed and the other one will get extended, right? It will get enlarged. So the whole aircraft will, when I apply this force, let me change its color. This whole aircraft will be doing like this. Agree? The whole aircraft will be seen in this position. Then after this spring gets compressed, let's say this spring here got compressed. Now this spring, the next spring got enlarged. Okay, what this will do? It will have the tension build up. Okay, and this spring will have the compressive force in it. So the K into whatever is the displacement of the spring is there, that thing will be KXD I am writing. Okay, no need to write that. Hope you are understanding. What this K into X will force it to do? K into XP and T will make the airplane pitch down. Okay, so you will see that this airplane, after a while, this airplane will be seen as a pitch down. Okay, so you'll be seeing this kind of setup of the oscillation. Hope this is clear. If you are monitoring, what happened?
Is it hinged at the center?
No, it's not the hinge. It is the CG. Okay. About the CG of the aircraft, it is doing that. Can we go ahead now?
Yes, sir.
Okay. So we are conducting a small experiment in our lab, and this is what is happening. What you will see in your lab, tell me. If you conduct this experiment in your laboratory, what you will experience. Suppose you are monitoring this point, or 1 second. Let me take this point. It is on the axis. So this point will be seen here, and after some time it was seen here. I made it to go. Yeah. You are observing that point, let's say. What you will see? This is the amplitude.
So the amplitude will decrease slowly with time.
In your lab, you will see that you did this, applied the force F for a moment. It was momentary. You will not apply this force continuously. Okay. So and then you want to see what is the observation. So after some time, what you will see is, sorry, what you will observe in these two things. I'm just going to make a neat figure. Just give me some time. Okay, because every book you will see only the waves, oscillations, and all. You understand what they basically mean. Okay, so you did this force of excitation. First, you went on the negative side. The displacement began here. Okay, then after that much of displacement, 1 second. Okay, after that displacement here, now it is left for the response of the aircraft. So this aircraft will try to come back to the equilibrium after getting displaced. Okay, it will move towards the equilibrium and it will overshoot the equilibrium position. Okay, in the first cycle you will see that the amplitude of oscillation was this big, same as this x naught. Okay, after a while, what you will see, the amplitude will get reduced, then further get reduced, then further get reduced, and it will come to the equilibrium. After a long time, when you come back after an hour or so, you'll see that the amplitudes of oscillation happened and the airplane is again in equilibrium and stationary. Why do you see that? What is resisting it? Why it is not continuing to oscillate? Anyone?
Inertia.
No. What do you mean by inertia?
Damping.
There is no damping. How?
Viscosity of the medium.
Correct. It is the because of the presence of the air. Okay. So every time when the airplane is going up, the air is resisting its motion. When it is coming down, air is resisting its motion. Suppose I have a laboratory in which, in a laboratory, let's say I have an, okay, no air friction, means no resistance offered by the medium. What will happen? Suppose I displace the aircraft.
Oscillation.
Suppose I displace my aircraft first like this, and I am observing this point. So my initial displacement is this. Hope you are getting my point. This is my F. I applied the force F and I will begin here. This is my initial displacement. Okay. If there is no air friction, what will happen?
The amplitude will remain same.
Correct. And the motion will become periodic. It will be like a simple harmonic motion. Agree? The time period between these two will be same as the time period between these two and this two. Okay? So the time period will you will be able to compute the time period of the oscillation. Can I go ahead now?
Yes,
So
sir.
this, if you write here no air friction, okay, so this is the experiment 1. You conducted the experiment 1, okay. So this will represent this kind of oscillation in which the amplitude of the oscillation here is x1 after one cycle. Then after the second cycle it is x2. After the third cycle it is x3. So here x1 is equals to x2, that is equal to x3, and so on. They all are constant. If the amplitude of oscillation is same, we say the system is dynamically neutral. Okay. What else can you say? Is it statically stable or unstable?
Stable.
Statically stable.
Correct. Okay. See, for example, the for the prerequisite for checking the dynamic stability, when you will check the dynamic airplane is dynamically stable or unstable, is it should be okay statically stable. If it is statically stable, then you will go for checking its dynamic. Okay. Statically unstable, suppose. Okay. If the airplane is statically unstable, okay, you will not check its dynamic. You won't check the dynamics of it. Hope you understand that. A system which is statically unstable will always be dynamically unstable. Can I go in?
Yes.
So I can write this system is if any system is executing this kind of thing, I can say it is statically, you see, every time it is trying to move towards the horizontal line. That is the equilibrium. In every cycle it is trying to do that. Okay. So it is all every time trying to go back to it is having the tendency to go back to the equilibrium position. That was this position. Okay. Now you write statically stable and and dynamically neutral system. Let's conduct now the second experiment. I'll be conducting next experiment now. Let me take this aircraft. So I'm not having air friction and I'm conducting an experiment. How do you remove the air from your room? You can put some set of suctions and make the least possible air, kind of pure vacuum. Conduct the experiment then. Okay. Now let's conduct another experiment. 1 second. Okay, I'll see to it later. Let's say I applied the force of excitation like this, but this time I'm incorporating two extra things in it. Okay. I'm using a damper. if I add a damper to it, here as well as here, suppose I connected a set of dampers with damping coefficient C. What you will observe? Will the figure be the same as this?
No, sir.
Will it be same or different?
Different.
Obviously, it should be different, right? How it will be different? You will not be getting the same amplitude. It will damp out the oscillation, right?
Yes, sir.
So this damper will reduce the amplitude of oscillation and the overall damping time will get reduced. So you will see the reduction in amplitudes of oscillation. Okay. Right. Draw this everybody with a damper. Hope you made this figure. Everyone?
Yes, sir.
Okay. Make this. And here you write. What can you say about this system now?
Statically
Dynamically
and
stable.
dynamically. Both dynamically stable.
Statically stable and dynamically
Dynamically stable.
stable system. Okay. Now there is an aircraft. Okay. There is an aircraft to which you gave the oscillation. You gave the means it started to execute the oscillation, but the response of the aircraft is like this. Means it went on increasing the amplitude. With time, the amplitude of oscillation started to increase. Instead of drawing it like that, I would like to draw it neatly. Just give me some time. Need not be symmetric, first of all. This could be something else. These two lines need not be symmetric. I'm just drawing my guidelines, you can say, to draw the neat figure. So the amplitude of oscillation, hope you can see, I took the lesser one here. Okay, need not be less also, it can be more also. So the amplitude of oscillation is increasing. Okay, so this is like x naught, then you can write x1, this you can write x2, this you can write x3, and so on. If the aircraft is doing this, what would you say?
Statically stable but dynamically unstable.
Correct. Write that. Statically stable. So one thing is very clear, that static stability will not guarantee the dynamic stability, but dynamically unstable. Can I go ahead now?
Yes, sir.
Come on, guys, finish this.
Yes, sir.
Okay, right. Next subheading you write second order differential equation. Most of the mechanical systems, their governing equations end up to be the second order differential equation. So you write many physical systems can be modeled by second order differential equation. Full stop. Right. For example, control servo motors, comma, special cases of aircraft dynamics, comma, as well as many mechanical systems are governed by second order differential equation. Second order differential equation. To illustrate the properties of a second order differential equation, we shall examine the motion of a mechanical system composed of a mass, comma, a spring and a damping device. Okay. Now you take a mass M, which is free to roll on this. Don't consider the friction of this. Leave the friction. The whole system is like this. The mass is free to roll on this. It is connected to a spring of stiffness K and a damping device with a damping constant C, damping coefficient C. Let's say there is a force of excitation which depends on the time T. Okay. If I draw the free body diagram of this body here, if I draw a free body diagram of this particular body, what do I get? This will be K into X, this will be C into X dot, and this will be F. This is the free body diagram, FBD, right? Hope you all are doing this in mechanical vibration in Saturday, Sunday's class. So this
Yes,
shouldn't
sir.
be a tough thing. It's well understood. dx by dt. X dot is dx by dt. Can I go ahead now?
Yes, sir.
Yes, sir.
Okay. The forces acting on the system are shown in figure. Full stop. The differential equation for this system can be written as right, the force equilibrium f of t minus kx minus cx dot equals to mx double dot. Okay, fine. This implies mx double dot plus cx dot plus kx is equals to f of t. So if I divide throughout by mass, what do I get? X double dot plus c by m x dot plus k by m x equals to capital F of t divided by m. Let this be small f of t. You can write or x double dot is d square x by dt square plus c by m into dx by dt plus k by m into x should be equal to f of t. Bracket this equation, name it as equation number 1. I need to charge my iPad. I'm left with only 4% of charge. Okay, you take a break of 15 minutes, guys, but do not log out. Okay, stay in it. Otherwise, I'll have to allow 140 people in the teams. Okay,
Okay, sir.
fine. You can mute yourself. Even I will do the same. Okay, 15 minutes break. So 8:37 we'll restart the session. We can have something like coffee or anything, food. Okay, bye guys.
Okay, sir.
Take a break.